There are moments in Earth's history when progress seems to stop. Life spreads, ecosystems stabilize, complexity grows, and then something changes. In the rock record, these moments appear as boundaries. Below them, one world, above them, another. More than 99% of all species that have ever lived are gone. Most disappeared gradually. But at several points in deep time, loss accelerated, entire ecosystems collapsed, dominant groups vanished. The fossil record shows long periods of stability, followed by sudden shifts that reshaped the planet's living systems. Antarctica once held forests. Ice once reached the tropics. Oceans have changed chemistry more than once. Life returns after these disruptions, but it does not return the same way, which raises a deeper question. Are these collapses accidents, or are they part of how Earth works? Why do periods of expansion so often end in erasure? How many times has the biosphere rebuilt itself from near ruin? And if resets shape the past, could they shape the future? Tonight, we follow the pattern written in stone, tracing the rhythm of flourishing and loss. But before we begin, if you're already enjoying this peaceful moment, it would mean the world to me if you gave this video a gentle like, maybe even subscribed, if you'd like more sleepy science stories like this. And if you'd be so kind, let me know in the comments, where are you winding down from tonight, and what time is it there? I love watching our little bedtime map light up, one dreamer at a time. So now take a breath, let your shoulders soften, and let's begin. Beneath layers of sandstone and limestone, time arranges itself in quiet order. Grain settles over grain, shell over shell, until entire ages rest compressed within stone. In those layers, life leaves impressions of its passing, not in motion, but in absence and return. Extinction, in its simplest sense, is disappearance, a species no longer living anywhere on Earth. Yet in the long rhythm of deep time, disappearance is not unusual. Background extinction moves steadily through the ages, a soft attrition shaped by competition, environmental shifts, disease, and chance. Most species persist for a few million years before fading. Their loss does not shatter ecosystems. It blends into the constant reshuffling that defines evolution. Forests thin and refill. Shorelines migrate. Creatures adapt or yield, and the overall tapestry remains intact. Scientists recognize this steady fading through fossils embedded in successive rock layers. A shell abundant in one stratum grows rarer in the next, then vanishes entirely. Bones that once appeared across continents cease to appear above a certain boundary. The pattern is never observed in a single outcrop alone, but across basins, across oceans, across continents. When the same absence repeats globally within the same slice of geological time, disappearance becomes measurable. Biodiversity in ancient worlds is traced not by counting individuals, but by counting kinds. Paleontologists tally genera and families preserved within rock layers, mapping how many distinct forms lived within a given interval. In stable periods, diversity fluctuates gently, rising and falling within a narrow range. The curve of life resembles a slow tide. A mass extinction is different in scale and speed. Instead of isolated losses, entire branches of the tree of life contract at once. Diversity drops sharply in the fossil record, often within a span that is brief in geological terms. Coral communities collapse across distant seas. Land ecosystems reorganize as dominant groups vanish together. Recovery, when it comes, unfolds over millions of years, not centuries. The distinction rests not only on numbers, but on ecological structure. During background extinction, food webs remain largely intact. During a mass extinction, the architecture itself fractures. Keystone organisms disappear, specialized relationships unravel. The fossil record records this fracture as an abrupt boundary, a thinning of forms followed by a sparse horizon where only a few survivors persist. Extinction, then, is both ordinary and extraordinary. It operates constantly in the background, shaping evolution with quiet persistence. At rarer intervals, it accelerates beyond its normal pace, transforming the biosphere in sweeping strokes. Within the stone, these pulses appear as sudden contractions in diversity, followed by gradual radiations of new forms that refill emptied niches. Through careful measurement of these patterns, scientists read extinction not as a single event, but as a spectrum. At one end, a steady fading woven into life itself. At the other, episodes where the balance tips sharply and the planet's living systems reorganize in ways that leave lasting marks in rock and memory. Long before mammals stirred in forest shadows, before coral reefs took their modern shape, the planet crossed a threshold almost too vast to imagine. Around 252 million years ago, near the close of the Permian period, the steady pulse of life faltered on a scale unmatched in the fossil record. In marine sediments laid down during that interval, diversity thins abruptly. Reef builders that had flourished for millions of years vanish from the layers above. Trilobites, long resilient and widespread, disappear entirely. Brachiopods, crinoids, ammonoids, whole communities woven through shallow seas, shrink to a fraction of their former variety. Estimates drawn from these records suggest that roughly 90% of marine species were lost. On land, the pattern echoes. Forest ecosystems reorganize. Insect lineages contract. Nearly 70% of terrestrial vertebrate species fade from view. The collapse was not confined to a single coastline or basin. Signals of upheaval appear in rock sequences across what are now separate continents, then joined in the vast supercontinent Pangaea. In many regions, dark layers rich in organic carbon accumulate, hinting at oceans that had grown depleted of oxygen. Some sediments contain minerals that form in warm, stratified waters, where circulation slows and deeper layers stagnate. The chemistry of shells records shifts in carbon isotopes, suggesting a profound disturbance in the global carbon cycle. Unlike the extinction that ended the age of dinosaurs, there is no universally accepted crater marking a single catastrophic impact. Instead, attention turns to the immense volcanic province known as the Siberian Traps. Over a span that was brief in geological terms, eruptions poured out vast volumes of basalt across what is now northern Asia. Lava spread in sheets hundreds of meters thick. Beneath the surface, magma intruded into carbon-rich sediments, potentially releasing enormous quantities of carbon dioxide and methane into the atmosphere. Climate models built around this interval describe rapid warming, acidifying oceans, and expanding zones of oxygen-poor water. On land, rising temperatures and shifting rainfall patterns would have strained ecosystems already adapted to specific seasonal rhythms. In the seas, elevated temperatures reduce the solubility of oxygen, tightening an already narrowing margin for complex organisms. Food webs dependent on stable plankton communities could have unraveled as foundational species declined. Recovery did not unfold quickly. In the layers that follow, biodiversity remains low for millions of years. Early Triassic ecosystems appear simplified, dominated by a handful of hardy survivors. Gradually, new groups radiate into emptied niches, exploring evolutionary pathways that had once been closed by competition. The Permian extinction stands not only as the most severe biological crisis known, but as an episode driven by forces that rose from within the planet itself. Fire from deep mantle plumes, gases released into air and sea, chemical balances tipped beyond familiar bounds. In stone, the boundary is stark. a narrow interval separating two different biological worlds, and beneath its quiet surface lingers the sense of processes far larger than any single cause. At the boundary between the Cretaceous and the Paleogene, a thin layer of clay appears in rock sections around the world, enriched with iridium, an element more common in meteorites than in Earth's crust. That quiet seam, no thicker than a finger in many places, marks the arrival of an object roughly 10-12 kilometers wide, descending from space toward a shallow sea that once covered what is now the Yucatan Peninsula. When it struck, the release of energy exceeded that of billions of nuclear bombs detonated at once. Rock at the point of impact vaporized instantly. A crater more than 100 kilometers across formed within minutes. Shock waves radiated through the crust, while molten droplets of ejecta were flung high above the atmosphere before arcing back toward the surface. As they re-entered, friction heated the sky, igniting widespread wildfires across distant continents. Soot from these fires, mixed with pulverized rock and sulfate aerosols, blasted from evaporite deposits at the impact site. The atmosphere thickened with fine particles that reflected and absorbed sunlight. In the weeks that followed, daylight dimmed, photosynthesis faltered in oceans and on land. Plankton populations declined sharply as surface waters cooled and darkened. On land, plants dependent on steady light cycles withered, and herbivores that fed upon them faced sudden scarcity. Food chains began to unravel from their base upward. Large, non-avian dinosaurs, many requiring vast amounts of vegetation to sustain their size, could not endure prolonged disruption. Predators that depended on them soon followed. Within months to years, entire ecological networks that had dominated for over 160 million years contracted dramatically. Yet not all life vanished. Small mammals, many no larger than modern shrews, persisted in sheltered niches. Their modest energy needs allowed them to survive on seeds, roots, and detritus when fresh foliage was scarce. Some burrowed underground, insulated from temperature extremes and fire. Birds, the feathered descendants of certain theropod dinosaurs, endured in reduced numbers, carrying forward a lineage that would later diversify in open skies. Crocodilians, turtles, and amphibians found refuge in aquatic environments less immediately devastated by surface fires. The extinction at this boundary was severe, but more selective than the crisis that closed the Permian. Approximately 75% of species disappeared, leaving empty ecological spaces across continents and oceans. In the aftermath, surviving groups expanded into roles once held by giants. Mammals diversified into forms adapted for grazing, climbing, swimming, and eventually thinking with larger and more complex brains. The asteroid impact stands as a sudden external shock, a contrast to slower internal upheavals driven by volcanism or shifting chemistry. In a geologic instant, dominance changed hands. The event reveals how survival is often linked not to size or power, but to flexibility and circumstance. From a layer of clay scarcely visible in outcrop, a new chapter in Earth's living history began to unfold, shaped by those small creatures that endured when the towering rulers of the Mesozoic quietly receded into stone. In certain intervals of deep time, the color of the seafloor changed. Sediments that once held the scattered remains of shells and reef fragments gave way to dark, finely laminated layers, rich in organic carbon and nearly empty of burrows. These black shales, spread across ancient continental margins, speak of waters that no longer breathed as they once had. Oxygen in the ocean is not constant. It enters at the surface, drawn from the atmosphere, and stirred downward by currents driven by wind and differences in temperature and salinity. In a stable system, cold, dense waters sink and carry dissolved oxygen into the depths, sustaining animals that move slowly along the seabed. When climate warms significantly, this circulation can weaken. Surface waters grow lighter and more stratified, forming layers that resist mixing. The deeper ocean becomes isolated, cut off from renewal. As temperatures rise, oxygen becomes less soluble in seawater. At the same time, higher metabolic rates in warmer conditions increase the demand for it. Organic matter sinking from surface blooms decomposes, consuming what little oxygen remains below. Zones of low oxygen expand, merging into broad regions where only specialized microbes endure. In extreme cases, the chemistry of the water shifts further still. In the absence of oxygen, certain bacteria turn to sulfate as an alternative energy source. Through their metabolism, they produce hydrogen sulfide, a gas toxic to most complex life. In modern seas, such conditions are largely confined to restricted basins, but during past crises, they appear to have spread more widely. Geochemical signatures in ancient rocks, including specific sulfur isotopes and biomarkers tied to green sulfur bacteria, suggest that hydrogen sulfide may have risen into sunlit surface waters in some intervals. For marine animals dependent on oxygenated habitats, the consequences were severe. Shell-bearing invertebrates struggled as their tissues encountered suffocating conditions. Fish and mobile predators faced shrinking zones of survivable water, compressed between warming surfaces and anoxic depths. Coral reefs, sensitive to both temperature and chemistry, faltered as foundational species declined. Food webs simplified, then fractured, leaving behind communities dominated by opportunistic survivors. The evidence of these episodes lies not in a single catastrophic layer, but in thick sequences of dark sediment deposited over thousands to millions of years. The absence of burrowing traces indicates that few organisms disturbed the seafloor. The concentration of preserved organic material reflects limited decay in oxygen-poor environments. Together, these features form a quiet record of oceans that had shifted from life-supporting basins to chemically altered expanses. Such transformations did not occur without cause. They were linked to broader disturbances in climate and carbon cycling, where volcanic emissions or other inputs increased greenhouse gases and pushed global temperatures upward. As surface waters warmed and stratified, the delicate balance that keeps deep oceans ventilated tipped gradually out of alignment. The sea did not empty all at once. It thinned, layer by layer, until vast regions became inhospitable. In that thinning, marine ecosystems contracted, and another chapter in Earth's pattern of disruption settled into stone. There were intervals when the planet reflected more sunlight than it absorbed, and with each passing season, the chill deepened. Continents that once felt rainfall and river flow grew locked beneath advancing ice. The oceans, too, began to seal over, their surfaces glazing with frozen crust that thickened year by year. Geologists call these intervals Snowball Earth, episodes during the Proterozoic eon when global temperatures appear to have fallen so far that ice may have extended from the poles toward the equator. Evidence for this deep freeze rests in unlikely places. In regions that were once tropical, ancient rocks contain glacial deposits, scratched and jumbled in ways that only moving ice can explain. Dropstones, fragments of rock carried by floating ice and later released into fine marine sediment, lie embedded within strata that formed at low latitudes. Paleomagnetic signatures, preserved in those layers, confirm that they were deposited far from the poles. As ice advanced, it increased Earth's reflectivity. Bright surfaces bounced solar energy back into space, amplifying cooling in a feedback loop that tightened its grip. With oceans capped, exchange of heat and gases between water and atmosphere diminished. Weathering rates slowed as rainfall decreased, altering the long-term balance of carbon between air, rock, and sea. The planet entered a new state of equilibrium, one starkly different from warm intervals that had come before. Life did not disappear entirely beneath this frozen canopy. Microbial communities likely persisted in pockets where liquid water remained. Near hydrothermal vents along the seafloor, geothermal heat sustained localized oases. There, chemical energy rather than sunlight fueled ecosystems anchored by chemosynthetic bacteria. Beneath thinner ice near the equator, cracks and leads may have allowed limited light penetration, supporting photosynthetic microbes adapted to dim conditions. Survival became a matter of endurance, confined to refuges shaped by heat and chemistry. The frozen state endured for millions of years, yet it did not last indefinitely. Volcanic eruptions continued to release carbon dioxide into the atmosphere. With weathering suppressed under ice, that carbon dioxide accumulated gradually, strengthening the greenhouse effect. Over long spans, atmospheric concentrations rose high enough to trap more heat than ice could reflect. Once melting began, darker ocean waters absorbed sunlight efficiently, accelerating thaw in a powerful reversal of the earlier feedback. The transition out of global glaciation may have been swift in geological terms. As ice retreated, meltwater poured into basins, altering salinity and circulation. Sediments deposited immediately above glacial layers often contain distinctive carbonate formations known as cap carbonates, recording rapid shifts in chemistry during deglaciation. From a world sheathed in ice, emerged seas open once more to currents and exchange. These extreme swings reveal a climate system capable of moving between states that differ profoundly in temperature and habitability. Ice at the equator and open tropical oceans represent endpoints of a dynamic balance, governed by feedbacks that can reinforce cooling or amplify warming. In the stone record, the traces of global frost sit quietly beside those of warmer ages, reminders that Earth's surface conditions have traversed vast ranges, reshaping the stage on which life persists. Across certain horizons in the geological record, layers of hardened basalt stack one upon another in immense thickness, stretching for hundreds of kilometers. These formations are not isolated volcanoes rising from singular cones, but vast provinces where molten rock once welled up through fractures in the crust and spilled outward in relentless sheets. The term flood basalt captures their scale, though the word flood hardly conveys the breadth of stone left behind. In what is now Siberia, in India, and in other ancient terrains, these eruptions unfolded over intervals lasting hundreds of thousands to millions of years. Lava did not pour continuously, yet it returned again and again, advancing in dark tides across landscapes that had supported forests, rivers, and soils. Each pulse added another layer, sometimes tens of meters thick, until the cumulative volume rivaled or exceeded that of entire mountain ranges. Regions larger than modern countries were entombed beneath basalt, reshaped into plateaus that still endure. Beneath the visible flows, magma intruded into sedimentary basins rich in organic material. As molten rock heated coal beds and carbon-bearing strata, gases were liberated in enormous quantities. Carbon dioxide rose steadily into the atmosphere, joined by sulfur dioxide and other volcanic emissions. Over extended periods, This persistent outgassing altered atmospheric chemistry, strengthening the greenhouse effect and shifting climate toward warmer states. With increased carbon dioxide came changes in rainfall patterns and temperature gradients. Enhanced evaporation intensified the hydrological cycle in some regions, while others experienced prolonged dryness. Sulfur compounds injected into the atmosphere combined with water vapor, producing acidic precipitation. Rain falling through these altered skies carried dissolved sulfuric and nitric acids, influencing soils and freshwater systems and adding further stress to living communities. The oceans responded to this sustained input of greenhouse gases. Elevated atmospheric carbon dioxide dissolved into surface waters, forming carbonic acid and lowering pH. Even modest shifts in acidity can interfere with the ability of marine organisms to construct calcium carbonate shells and skeletons. Over extended intervals of volcanic activity, such chemical stress would have compounded the effects of warming and altered circulation, pressing marine ecosystems beyond familiar thresholds. Unlike a sudden impact from space, flood basalt events represent crises that accumulate through persistence. Each eruption may have seemed isolated in time, separated by decades or centuries, yet over geological spans they formed a near continuous disturbance. The sky, repeatedly illuminated by distant fissures, carried fine ash and aerosols that dispersed globally. Climatic systems adjusted incrementally, then crossed into new regimes as cumulative forcing mounted. In the quiet persistence of these eruptions lies their power. They reveal how internal heat, rising through mantle plumes and fractures, can reshape surface environments without a single dramatic moment. Stone upon stone records the passage of lava. Subtle shifts in isotopes and mineral assemblages testify to atmospheric and oceanic change. Over long stretches, the sky itself became part of the mechanism, bearing gases that altered the balance of air and sea, while life navigated conditions increasingly unlike those that had once seemed stable. In the aftermath of upheaval, the fossil record often reveals a quiet shift in scale, where large bodies once dominated landscapes and shorelines, smaller forms become more common in the layers that follow. It is not a sudden rule imposed from above, but a pattern that appears again and again when environments destabilize. Size carries advantages in stable worlds. Larger animals can travel farther in search of resources, deter predators, and regulate body temperature with greater inertia. Yet those same traits come with high energy demands. A massive herbivore requires a constant and abundant supply of vegetation. A large predator depends on a network of prey species, each one supported by plants or plankton below. When disruptions ripple through climate or chemistry, these energy pathways narrow. Productivity declines at the base of the food web, and the strain moves upward. Smaller creatures exist closer to the foundation of that web. Many consume seeds, detritus, insects, or microorganisms. Their caloric needs are modest by comparison, allowing them to persist on limited or shifting resources. In times of scarcity, a diet that includes a broad array of foods provides resilience. Specialists, finely tuned to a single source of nourishment or habitat, may struggle when that niche contracts. Generalists, able to adjust their feeding strategies, often endure. Shelter also shapes survival. Burrowing mammals, amphibians, and invertebrates can retreat below the surface, where temperatures fluctuate less dramatically and direct exposure to wildfire, ash, or frost is reduced. Aquatic organisms in rivers, lakes, or deeper marine settings may find temporary refuge from surface extremes. Even within devastated ecosystems, microhabitats persist, offering pockets of stability amid wider change. Reproductive strategies contribute to this pattern as well. Species that mature quickly and produce numerous offspring can rebound from population losses more rapidly than those that invest heavily in a small number of young. In turbulent periods, rapid life cycles allow natural selection to act swiftly, favoring traits suited to altered conditions. Over successive generations, adaptability becomes visible in the fossil record as new forms radiate from modest beginnings. This does not imply that small size guarantees survival, nor that large organisms invariably vanish. Rather, it highlights a relationship between biological scale and environmental volatility. When systems remain steady over long intervals, larger and more specialized creatures can thrive, supported by intricate networks of dependency. When those networks fracture, flexibility and lower energy thresholds become valuable assets. Across multiple extinction events, from deep marine crises to continental transformations, similar shifts in community structure unfold. Dominant giants recede, and ecosystems rebuild around smaller, often overlooked survivors. Through these recurring transitions, a subtle pattern emerges, suggesting that resilience in changing worlds is frequently rooted not in strength or stature, but in adaptability, economy, and the capacity to persist within constrained margins. An ecosystem can appear complete even as its balance depends on only a few quiet anchors. Certain species shape their surroundings far beyond what their numbers alone would suggest. They are not always the largest or most visible, yet their presence organizes the relationships around them. When such a species diminishes or disappears, the change does not remain isolated. In coral reef communities, reef-building corals create the physical structure that shelters fish, crustaceans, and countless other organisms. In forests, large herbivores influence plant composition through grazing patterns, while predators regulate those herbivores in turn. Along rocky coasts, sea stars that prey upon mussels prevent a single species from monopolizing space. These organisms function as keystones, maintaining diversity by holding competitive forces in balance. When disturbance removes a keystone, whether through climate stress, chemical alteration, or sudden catastrophe, the surrounding web begins to loosen. Without predators, certain prey populations may expand rapidly, consuming vegetation or smaller animals at unsustainable rates. Without primary producers capable of stabilizing habitat, shelter, and breeding grounds decline. One shift triggers another, often in sequences that ripple outward across trophic levels. The breakdown of food webs is rarely uniform. Some species decline immediately as their resources vanish. Others persist temporarily, sustained by stored energy or adaptable diets, only to falter later as secondary effects accumulate. Scientists studying past collapses observe this pattern in staggered losses recorded within stratified rock. Initial disappearances are followed by further reductions in diversity as ecological networks fragment. Cascading extinctions amplify the original disturbance. The removal of a foundational organism alters nutrient cycling, sediment stability, and patterns of energy flow. Microbial communities may change composition, influencing soil fertility or water chemistry. In marine settings, the loss of plankton can reduce oxygen production and carbon sequestration, compounding physical stresses already underway. Each connection within the web represents both resilience and vulnerability, strength when intact, fragility when broken. Ecosystems unravel not as dramatic explosions but as gradual separations. Interdependent relationships dissolve, and complexity contracts into simpler arrangements. Where once multiple pathways existed for energy to move from sunlight to herbivores to predators, fewer routes remain. The system becomes less buffered against further change. With diminished redundancy, additional stresses encounter little resistance. In the fossil record, such unraveling appears as reduced diversity within communities, shifts in species composition, and the disappearance of specialized forms. Reefs transform into microbial mounds. Forests give way to open landscapes, dominated by hardy generalists. These transitions reflect the internal dynamics of networks that have lost key stabilizing elements. Through repeated episodes in Earth's history, the domino effect reveals a consistent principle. Life organizes itself into intricate webs, yet those webs rely on pivotal threads. When external forces sever those threads, collapse can propagate beyond the initial trigger, reshaping entire biomes. Over time, new keystones emerge and networks rebuild, but the interim bears the imprint of a system momentarily unbound from its former structure. There are spans in Earth's history when temperature does not drift gently upward or downward, but shifts with abrupt intensity, as though the balance has tipped and momentum carries the system into a new state. In sediments and ice cores, these changes appear not as gradual gradients, but as sharp inflections, marking intervals when climate moved faster than ecosystems could comfortably follow. Rapid warming events have punctuated deep time. During certain episodes, global temperatures rose several degrees within a few tens of thousands of years, a brief instant in geological terms. Carbon isotopes preserved in marine sediments record sudden injections of greenhouse gases, while fossil assemblages reveal poleward expansions of warmth-loving species. Tropical plants appear at higher latitudes, and marine organisms accustomed to cooler waters retreat toward shrinking refuges. Ocean chemistry adjusts alongside temperature, altering nutrient cycles and oxygen distribution. Cooling, too, has advanced swiftly at times. The onset of major glacial intervals transformed landscapes with advancing ice sheets, lowering sea levels and reorganizing coastlines. As glaciers expanded, reflective surfaces increased, reinforcing further cooling. Grasslands replaced forests in some regions, and arid belts shifted as atmospheric circulation patterns realigned. Species adapted to warmth encountered narrowing habitats, while cold-tolerant organisms spread into newly opened terrain. The contrast between greenhouse worlds and icehouse states illustrates the breadth of Earth's climatic range. In greenhouse intervals, polar regions support temperate forests, and sea levels rise as ice diminishes. In icehouse phases, vast sheets of ice lock away water, exposing continental shelves and altering ocean currents. These states are not static endpoints, but expressions of a dynamic equilibrium shaped by orbital variations, tectonic rearrangements, volcanic emissions, and feedbacks within the carbon cycle. For living communities, the speed of transition often matters more than the direction. Organisms possess physiological limits, thresholds beyond which enzymes, reproductive cycles, and structural adaptations falter. Migration offers one response, allowing populations to track favorable conditions across shifting latitudes or elevations. Fossil pollen records demonstrate forests advancing and retreating over centuries, following temperature gradients. Marine species shift their ranges along coastlines or into deeper waters as thermal boundaries migrate. Yet migration is constrained by geography and timing. Mountain ranges, deserts, and expanding ice can block pathways. Rapid changes compress habitats faster than dispersal can compensate, leaving some species isolated in shrinking pockets. Adaptation through evolutionary change requires generations, and when environmental shifts outpace reproductive cycles, resilience is tested. Climate whiplash, whether warming or cooling, reveals the sensitivity of ecosystems to the tempo of change. Gradual adjustments can be integrated into the fabric of life, allowing communities to reorganize without complete collapse. Swift oscillations, by contrast, impose pressures that cascade through food webs and biogeographic patterns. In the record of rocks, shells, and leaves, these transitions leave their imprint as reorganized assemblages, testimony to a planet whose atmosphere and oceans are capable of moving between states with a force that reshapes the living world. Carbon moves quietly through Earth's systems, seldom visible, yet constantly exchanged among air, water, stone, and living tissue. In the atmosphere, it resides primarily as carbon dioxide, a trace gas with disproportionate influence. Plants draw it inward during photosynthesis, weaving carbon into leaves, wood, and roots. When organisms respire or decay, much of that carbon returns to the air, continuing a cycle that links breath to soil and sunlight to structure. Oceans absorb a significant share of atmospheric carbon dioxide, dissolving it into surface waters. There, it forms carbonic acid, which can separate into bicarbonate and carbonate ions. Marine organisms use these ions to construct shells and skeletons of calcium carbonate, storing carbon within their hard parts. When they die, some of that material sinks, accumulating on the seafloor as sediment. Over immense spans of time, burial and lithification transform these sediments into limestone and other carbonate rocks, locking carbon away within Earth's crust. Tectonic processes eventually return portions of this stored carbon to the surface. Subducted oceanic crust, rich in carbonates, descends into the mantle where heat and pressure liberate carbon dioxide. Volcanic eruptions release it back into the atmosphere, completing a long geological loop that can span millions of years. Weathering of exposed rocks counters this return. Rainwater, slightly acidic from dissolved carbon dioxide, reacts with silicate minerals, drawing carbon from the air and transporting it as dissolved ions to the ocean, where it may again become part of carbonate sediments. Under stable conditions, these fluxes maintain a balance that regulates global temperature. The carbon cycle acts as a thermostat, with weathering rates adjusting gradually in response to climatic shifts. When carbon input increases slowly, the system often compensates over long intervals, restoring equilibrium through enhanced rock weathering and sedimentation. Stress arises when carbon enters the atmosphere more rapidly than these buffering mechanisms can respond. Large volcanic episodes, methane releases from destabilized hydrates, or rapid combustion of organic matter can elevate atmospheric carbon dioxide within relatively short spans. Surface temperatures rise as the greenhouse effect intensifies, altering evaporation, precipitation, and ocean circulation. Warmer water holds less dissolved carbon dioxide and less oxygen, influencing marine chemistry and biology simultaneously. Feedback loops can amplify these initial changes. As temperatures climb, permafrost or marine sediments may release additional methane, a potent greenhouse gas. Reduced ice cover lowers planetary reflectivity, increasing absorption of solar energy. Drought and wildfire can diminish vegetation that would otherwise absorb carbon, allowing more to remain in the atmosphere. Each response reinforces the warming that triggered it. In the geological record, carbon stress appears as shifts in isotopic ratios, indicating injections of isotopically light carbon into the system. These signatures coincide with intervals of climatic upheaval and ecological turnover. Through such markers, scientists trace episodes when the ordinarily measured exchange of carbon accelerated beyond its usual pace, pushing climate into states that reshaped habitats worldwide. Within this intricate cycle, stability depends not only on total carbon, but on the speed at which it moves between reservoirs. Far beneath the surface of the ocean, where sunlight never reaches and pressure presses with quiet force, methane lies trapped in an unusual form. It is not free gas drifting upward, but methane hydrate, a crystalline lattice in which water molecules encase methane within cages of ice. Stable only under specific conditions of low temperature and high pressure, these deposits rest along continental margins and within sediments of the deep sea, stored in quantities that rival or exceed the carbon currently circulating in the atmosphere. For long intervals, hydrates remain locked in place, a silent reservoir beneath layers of mud and sand. The stability of this frozen structure depends on the balance between pressure and temperature. When ocean waters warm, even slightly, that balance can begin to shift. Heat diffusing downward through sediment alters the stability zone, thinning the layer where hydrates can persist. As ice-like structures destabilize, methane is freed as gas. Released methane may dissolve in surrounding water or rise in bubbles toward the surface. Some of it is consumed by microbes that oxidize methane into carbon dioxide, drawing oxygen from seawater in the process. In certain circumstances, however, methane can reach the atmosphere before being fully oxidized. Because methane is a far more potent greenhouse gas than carbon dioxide over short timescales, its arrival in the atmosphere can enhance warming significantly. This amplification effect creates a feedback. Initial warming, perhaps triggered by volcanic emissions or changes in ocean circulation, promotes hydrate destabilization. Methane release intensifies the greenhouse effect, raising temperatures further and potentially destabilizing additional hydrates. In sediment cores and isotopic records, such episodes may appear as rapid excursions in carbon signatures, marking the injection of carbon that bears the isotopic fingerprint of methane derived from organic sources. Geological studies of past warming events, including intervals marked by abrupt temperature rise and ocean acidification, often consider methane hydrates as a contributing factor. The Paleocene-Eocene thermal maximum, for example, exhibits carbon isotope shifts consistent with a rapid release of isotopically light carbon, though the exact proportion sourced from hydrates remains debated. What emerges clearly is that the seafloor contains reservoirs capable of influencing atmospheric composition when disturbed. Beyond atmospheric effects, methane oxidation within the ocean consumes oxygen and produces carbon dioxide, contributing to localized acidification and expanding zones of reduced oxygen. In this way, hydrate destabilization links ocean chemistry to atmospheric change, coupling processes above and below the sea. The presence of methane hydrates illustrates how Earth's systems hold latent potential for swift transformation under altered conditions. Beneath calm ocean surfaces, carbon can reside for millions of years in a delicate crystalline balance. When climate shifts, that balance may falter, releasing gases that reinforce the very warming that triggered their escape. Within this interconnected network, reservoirs and feedbacks intertwine, shaping the trajectory of climate and the living systems that depend upon it. The surface of the planet moves with patience too slow to witness in a single lifetime, yet across millions of years that motion rearranges the geography of life. Continents do not remain fixed. They converge, collide, fragment, and wander apart, carried atop plates that glide over the ductile mantle beneath. When land masses assemble into supercontinents, coastlines shrink and interiors expand. During the time of Pangaea, vast regions lay far from moderating ocean influence. Inland climates grew more extreme, with hotter summers and colder winters, and rainfall patterns shifted across newly formed mountain ranges. River systems altered their courses, and shallow epicontinental seas that once supported diverse marine communities retreated as continental shelves merged. Ocean currents respond to these rearrangements. The positions of continents determine the pathways available for surface and deep water circulation. When gateways between basins close, currents that once redistributed heat are redirected or halted. Conversely, the opening of new seaways allows water masses to exchange properties, influencing temperature gradients and nutrient transport. Such changes can alter regional climates and reshape marine ecosystems by modifying the distribution of oxygen and plankton productivity. As continents rift apart, isolation becomes a powerful force in evolution. Populations separated by widening oceans or rising mountain belts diverge genetically over time. Distinct faunas emerge on different land masses, adapted to local conditions. The breakup of Gondwana, for example, contributed to the unique assemblages of mammals, birds, and plants that later characterized South America, Africa, Australia, and Antarctica. Isolation fosters diversification, yet it also limits dispersal when environments change. Habitat extent expands and contracts with shifting shorelines and tectonic uplift. When sea levels fall or continents merge, shallow marine habitats diminish, reducing the area available for reef builders and coastal organisms. Conversely, periods of high sea level flood continental margins, creating new niches in warm, shallow waters. Mountain building can generate fresh environments through elevation gradients while also fragmenting existing ecosystems and restricting migration routes. Tectonic activity influences atmospheric composition indirectly as well. The uplift of mountain ranges accelerates chemical weathering, drawing carbon dioxide from the atmosphere and contributing to long-term cooling. Volcanic arcs associated with subduction zones release gases that may enhance warming. Thus, continental drift participates in regulating climate over geological timescales, shaping the backdrop against which extinction and radiation unfold. In the fossil record, these tectonic motions manifest as patterns of similarity and difference among distant regions. Identical species found on once connected continents testify to former proximity, while sudden divergence marks separation. The distribution of coal beds, reefs, and glacial deposits traces ancient latitudes and climates, revealing how rearranged geography influences ecological possibilities. Continental drift alters not only the configuration of land and sea, but the connectivity that allows life to move and adapt. By redefining coastlines, currents, and corridors, tectonics sets new boundaries and opportunities. Over deep time, this slow choreography becomes a quiet architect of both stability and disruption, guiding the conditions within which ecosystems either persist or yield to transformation. The edge between land and sea has never been fixed. Over geological time, shorelines advance and retreat in response to shifting volumes of ocean water and the slow rise and fall of continents. When sea level rises, waves move inland, flooding river valleys and spreading across low-lying plains. When it falls, shallow basins drain, exposing seafloor that once teemed with marine life. Shallow seas are among the most productive environments on the planet. Sunlight penetrates easily to the bottom, nourishing algae and seagrasses that anchor food webs. Coral reefs flourish in these illuminated waters, building intricate frameworks of calcium carbonate that shelter fish, mollusks, and countless invertebrates. Coastal wetlands filter nutrients and provide nurseries for juvenile organisms that later disperse into open water. The breadth of these habitats depends closely on the position of the shoreline. During intervals of rapid warming or glacial retreat, melting ice sheets add substantial volumes of water to the oceans. Thermal expansion further raises sea level as warming water occupies more space. Low-lying coastal regions become submerged, altering salinity gradients and sedimentation patterns. In some cases, the transgression of the sea creates new habitats inland. In others, especially where topography is steep or human modification constrains migration, ecosystems struggle to shift quickly enough to survive. Conversely, during cooling episodes when ice accumulates on continents, sea level can drop by tens to more than 100 meters. Vast expanses of continental shelf emerge, transforming shallow marine ecosystems into exposed plains. Reef structures that once thrived in clear, warm water may be left high and dry, subject to erosion and weathering. Organisms specialized for narrow depth ranges face abrupt loss of habitat. Reefs are particularly sensitive to both sea level and water chemistry. If the rise of the ocean outpaces the vertical growth of coral colonies, reefs may drown beneath deeper, less illuminated water. Changes in temperature and acidity compound the challenge, impairing calcification and weakening structural integrity. Fossil reefs preserved in ancient strata record episodes of flourishing, followed by intervals of decline, often correlated with shifts in sea level and climate. Coastal ecosystems form intricate networks linking terrestrial and marine realms. Mangroves and salt marshes buffer storm surges and stabilize sediments. Estuaries host complex communities, adapted to fluctuating salinity. When sea level changes rapidly, these transitional zones can contract or relocate, reshaping nutrient cycles and species distributions. Sedimentary records capture these transitions as shifts from marine to terrestrial deposits, or vice versa, marking boundaries between ecological states. Sea level rise and fall operate not merely as background fluctuations, but as drivers of ecological reorganization. The availability of shallow, sunlit habitat expands and contracts with these movements, influencing biodiversity on continental scales. In the layers of rock, successive marine and terrestrial sediments testify to the restless margin between land and sea, and to the communities that flourished or faded as that margin wandered across the surface of the earth. When paleontologists arrange extinction rates along a timeline stretching hundreds of millions of years, the curve does not form a smooth and steady decline. Instead, it rises and falls in irregular pulses. Some researchers, examining these fluctuations with statistical tools, have suggested that the peaks may not be entirely random. In several analyses, a recurring interval of roughly 26-30 million years appears between clusters of heightened extinction intensity. This proposed rhythm emerges from large databases cataloging fossil occurrences and disappearances. By assigning ages to stratigraphic boundaries and calculating rates of biodiversity loss, patterns begin to surface that invite interpretation. Statistical models, including spectral analysis and time series methods, have been applied to detect periodic signals embedded within the broader noise of geological history. In some iterations of these studies, a recurring pulse seems to echo faintly across deep time. Yet the interpretation of such patterns remains contested. The fossil record is incomplete, shaped by uneven preservation, sampling biases, and revisions in geologic dating. Changes in stratigraphic resolution can alter the apparent timing and magnitude of extinction events. Some statisticians argue that when uncertainties in age assignments are fully considered, the periodic signal weakens or disappears. The clustering of events may reflect the way data are grouped rather than an underlying cycle within Earth systems. Others maintain that even after accounting for biases, a subtle regularity persists. They propose mechanisms that might generate such pacing, ranging from mantle plume cycles deep within the Earth to astronomical influences that perturb comets in the outer reaches of the solar system. Hypotheses have included vertical oscillations of the solar system through the galactic plane, potentially increasing impact frequency at intervals. Each suggestion extends the scale of inquiry beyond isolated events, seeking a metronome beneath apparent randomness. Part of the challenge lies in distinguishing signal from coincidence. Over spans of hundreds of millions of years, random clustering can mimic periodicity, especially when the number of major extinction events is limited. Statistical significance depends on methodological choices, the length of the dataset, and the thresholds used to define what constitutes a pulse. As new fossil discoveries refine timelines and radiometric dating improves precision, earlier conclusions are often revisited. The question of hidden timing does not rest solely on mathematics. It touches on how the planet's internal and external drivers interact across vast intervals. If a regular pulse exists, it would suggest an underlying process capable of modulating environmental stability at grand scales. If not, then the pattern of extinction may arise from complex interactions without fixed cadence. Within the quiet graphs and layered rocks, the debate continues. The possibility of rhythm, whether faint or illusory, adds another dimension to the unfolding narrative. Between clear catastrophes and gradual change, there may or may not be a subtle tempo, a recurring swell in the long symphony of Earth's transformations. Far below the crust, beyond the reach of oceans and continents, heat continues to move through the mantle in slow convection currents. This internal energy is a remnant of planetary formation and radioactive decay, diffusing upward across immense spans of time. Though hidden from view, it exerts a steady influence on the surface above, shaping landscapes and climates through processes that originate deep within Earth's interior. Mantle plumes rise as columns of anomalously hot rock, buoyant against surrounding material. When such plumes approach the base of the lithosphere, they can thin and fracture the crust, allowing magma to reach the surface. Over millions of years, repeated eruptions build volcanic provinces or island chains aligned with plate motion. The Hawaiian Islands mark one modern example, though older and more expansive plume events have produced vast plateaus of basalt that altered atmospheric composition and climate. These volcanic pulses are not continuous flows but episodic surges. Magma chambers fill and erupt, pause and resume, creating sequences of lava and ash that accumulate layer upon layer. Each pulse releases gases stored within molten rock, including carbon dioxide and sulfur compounds that enter the atmosphere. Over extended intervals, such emissions can adjust global temperatures and influence ocean chemistry, reinforcing the interconnectedness between deep mantle processes and surface environments. Tectonic recycling complements plume activity. Oceanic crust forms along mid-ocean ridges as mantle material rises and partially melts. Over time, this crust cools, becomes denser, and eventually descends at subduction zones, carrying sediments and water back into the mantle. There, materials are transformed under pressure and heat, contributing to volcanic arcs and continental growth. Through this cycle, elements such as carbon and sulfur are exchanged between Earth's interior and exterior reservoirs, modulating atmospheric composition across geological time. Internal heat also drives the assembly and breakup of continents. As plates converge, mountains rise, altering weather patterns and enhancing chemical weathering. As they diverge, rift valleys form, opening new ocean basins that redirect currents and reshape habitats. These processes unfold gradually, yet their cumulative effects redefine the geography upon which ecosystems develop and evolve. The deep Earth engine operates without urgency, guided by thermodynamics rather than season. Its rhythms are measured in millions of years, yet their consequences register in extinction horizons and evolutionary radiations. Magma ascending through fractures, crust descending into darkness, continents drifting across latitudes, all arise from the same interior vitality. Surface life adapts to conditions that seem external and immediate, but many of those conditions originate far below. Climate fluctuations, atmospheric composition, and sea level shifts are intertwined with mantle convection and tectonic motion. In this way, the planet's inner heat becomes an architect of biological opportunity and constraint. Beneath forests, reefs, and plains, a slow circulation persists, shaping the stage upon which life appears, vanishes, and returns in altered form. Above every shifting continent and restless ocean, a steadier force radiates outward without pause. The Sun, a main sequence star fusing hydrogen into helium at its core, changes so slowly that its variability escapes ordinary perception. Yet, over spans measured in billions of years, its luminosity has not remained constant. Stellar physics indicates that as hydrogen in the core is converted to helium, the core gradually contracts under gravity. This contraction increases pressure and temperature, accelerating fusion rates. The result is a slow but steady rise in solar output. Models suggest that since Earth first formed, the Sun has brightened by roughly 30%. In earlier eons, when the planet received less energy, greenhouse gases likely played a crucial role in maintaining liquid water at the surface. This incremental brightening continues. Each million years adds a fraction more energy to the top of Earth's atmosphere. On short timescales, volcanic activity, orbital variations, and ocean circulation dominate climate patterns. On the deepest scales, however, solar evolution exerts a persistent influence, nudging baseline temperatures upward across eras. The difference is subtle within any single epoch, yet cumulative over immense intervals. As luminosity increases, Earth's climate system must adjust. Enhanced solar radiation intensifies evaporation, potentially strengthening the hydrological cycle. Chemical weathering of rocks accelerates in warmer, wetter conditions, drawing carbon dioxide from the atmosphere and providing a stabilizing feedback that tempers long-term warming. Over hundreds of millions of years, this interplay between solar forcing and geochemical response has helped maintain surface conditions compatible with life. Yet, the buffering capacity of the carbon cycle is not infinite. Projections into the distant future indicate that continued brightening will eventually overwhelm stabilizing feedbacks. Within roughly 1 to 2 billion years, solar energy may rise enough to trigger a moist greenhouse state. In such a regime, increased water vapor in the upper atmosphere could lead to gradual hydrogen loss to space, reducing ocean volume over geological time. Even without immediate ocean evaporation, ecosystems would confront temperatures beyond the tolerance of complex multicellular life. These changes unfold far beyond human time horizons. They belong to planetary history, written on the scale of eons. Compared with abrupt extinctions or volcanic pulses, solar brightening is almost imperceptible, a background drift rather than a sudden shock. Still, it frames the boundaries within which Earth's dynamic systems operate. The steady increase in solar output reminds us that the conditions sustaining life are neither fixed nor guaranteed indefinitely. The interplay between stellar evolution and planetary feedbacks has allowed habitability to persist through dramatic internal and external upheavals. Over billions of years, the sun's quiet intensification has shaped atmospheric composition, ocean chemistry, and the long arc of biological possibility. Even as tectonics churn and climates oscillate, the star above provides a gradually shifting backdrop, guiding the slow transformation of Earth's surface environment. In the long archive of stone and bone, continuity can give the illusion of permanence. A species appears in layer after layer, spanning what to us would be unimaginable ages, and it is tempting to view that persistence as stability. Yet even the most enduring lineages occupy only brief chapters within the broader sweep of life's history. Paleontological surveys suggest that most species persist for only a few million years before disappearing, replaced by close relatives or entirely new forms. This pattern unfolds quietly. Within a stable ecosystem, forests maintain familiar compositions, reefs retain their architectures, and predator and prey coexist in balanced proportions. Generations succeed one another with minimal, visible change. The boundaries of habitats remain recognizable, and the seasonal cycles repeat. On human timescales, such constancy feels enduring. On geological timescales, it represents only a momentary alignment of variables. Species are defined not only by their traits, but by the environmental envelopes in which those traits function effectively. Temperature ranges, atmospheric composition, ocean chemistry, and geographic connectivity all shape the conditions within which organisms thrive. As long as these parameters remain within tolerable bounds, communities can persist with subtle shifts in abundance rather than abrupt turnover. Beneath that apparent equilibrium, however, processes continue to evolve. Continents drift slowly across latitudes, altering climate gradients. Volcanic outgassing and weathering adjust atmospheric composition. Orbital cycles redistribute solar energy across hemispheres. Within ecosystems themselves, competition and adaptation steadily modify interactions. These gradual influences accumulate, sometimes imperceptibly, until thresholds are approached. Long intervals of calm can mask the steady buildup of stress. A warming trend measured in fractions of a degree per millennium may seem negligible within any given century. Yet, across hundreds of thousands of years, it reshapes climate zones. Incremental shifts in ocean chemistry alter the resilience of marine calcifiers, even if reefs continue to stand. Subtle habitat fragmentation driven by tectonics or sea level change may restrict gene flow long before extinction becomes visible in the fossil record. When thresholds are crossed, the transition from persistence to decline can appear abrupt. A lineage that endured for millions of years may vanish within a narrow stratigraphic band. The illusion of permanence dissolves, revealing that stability was conditional rather than absolute. In this context, ecosystems resemble dynamic balances rather than static structures. They are maintained by continuous feedback between organisms and environment, each influencing the other. As long as perturbations remain within certain limits, the system absorbs them. When cumulative pressures exceed adaptive capacity, reorganization follows. Across deep time, the rarity of true stability becomes evident. Periods of relative calm punctuate a broader narrative of change. Species rise, persist briefly in geological terms, and fade, while communities reorganize around new combinations of traits. Beneath the surface of apparent equilibrium, Earth's systems remain in motion, preparing the conditions under which continuity yields to transformation. After the sharp boundaries that mark collapse, the rock record does not return to what came before. Instead, it opens into intervals of sparse diversity, where only a handful of lineages occupy ecological space, once crowded with complexity. From these reduced communities, recovery begins, not by restoring lost worlds, but by building unfamiliar ones. In the wake of extinction, surviving organisms inherit landscapes stripped of former competitors and predators. Ecological niches remain vacant, their resources unclaimed. Over successive generations, populations expand into these open roles. This process, known as adaptive radiation, unfolds as descendants diversify rapidly in morphology and behavior, shaped by natural selection acting on variation already present within their gene pools. The fossil record captures these radiations as bursts of branching lineages following extinction horizons. Mammals, once small and largely nocturnal, diversified widely after the disappearance of dominant reptiles, evolving into forms suited for grazing, climbing, swimming, and gliding. In earlier eras, after marine crises reduced reef communities, new coral groups and reef-building organisms emerged, constructing different architectures from those that preceded them. Recovery did not replicate previous assemblages. It assembled new configurations. Evolution after collapse often introduces body plans or combinations of traits that were previously minor or absent. Freed from competitive constraints, organisms experiment across ecological possibilities. Some radiations explore new feeding strategies, exploiting resources that had been marginal before. Others alter developmental pathways, producing structural innovations that open fresh, adaptive landscapes. These changes accumulate gradually, but in geological perspective, they appear as swift expansions following prolonged scarcity. The pace of diversification varies with environmental stability. When climate and chemistry settle into relatively consistent states, evolutionary experimentation flourishes. Speciation rates increase, and morphological disparity broadens. In some intervals, entirely novel groups arise, redefining ecosystems for millions of years. Yet even during periods of growth, recovery remains incomplete in a historical sense. Certain lineages lost during extinction events never reappear, leaving permanent gaps in life's tapestry. Recovery also reshapes interactions among organisms. Predator and prey relationships reestablish under new parameters. Symbiotic associations form between survivors, and nutrient cycles reorganize around altered community structures. These emergent systems may differ substantially from their predecessors in resilience, productivity, and geographic distribution. The distinction between recovery and reversal becomes clear when comparing pre- and post-extinction assemblages. Though diversity may eventually reach or exceed former levels, the identities of the dominant groups shift. Trilobites gave way to new arthropod lineages. Giant reptiles yielded to mammals and birds. Extinction acts less as a reset button than as a pivot point, redirecting evolutionary trajectories into alternative pathways. Across deep time, this pattern repeats. Collapse trims the branches of the tree of life, while recovery encourages new growth from those that remain. The shape of that growth reflects both contingency and opportunity, producing ecosystems that echo the past only in their function, not in their composition. Life persists, yet it does so by transforming rather than retracing its steps. In the quiet intervals following mass extinction, the most conspicuous absence is often what once dominated. After the fall of the non-avian dinosaurs, terrestrial ecosystems were left without their largest herbivores and apex predators. Forest canopies, floodplains, and open plains no longer supported the towering bodies that had defined them for more than 100 million years. Into these newly vacant spaces moved creatures that had long existed in the margins. Mammals were not new arrivals to the Cenozoic world. They had persisted alongside dinosaurs, generally small, nocturnal, and ecologically constrained. When extinction reshaped the biosphere, ecological niches opened across multiple trophic levels. With fewer competitors and predators, mammals expanded in size, diet, and behavior. Some lineages evolved into large herbivores grazing on newly spreading grasslands. Others became swift carnivores, arboreal specialists, burrowers, and eventually marine dwellers that returned to the sea. Several biological traits supported this expansion. Mammals possess endothermy, the ability to generate internal heat through metabolism. This warm-blooded physiology allows activity across a wide range of temperatures and facilitates occupation of higher latitudes and variable climates. After climatic instability, the capacity to maintain stable body temperatures offered resilience where strictly ectothermic organisms might have faced seasonal constraints. Reproductive strategies also played a role. Live birth in most mammals, combined with parental care and lactation, increased offspring survival rates in fluctuating environments. Young could develop in protected internal conditions, buffered from some external stressors. Extended care allowed learning and social behaviors to shape survival, embedding adaptability within development rather than leaving it solely to instinct. Brain size and neural complexity further distinguished many mammalian lineages. Enlarged cerebral cortices supported sophisticated sensory processing, memory, and problem solving. Flexible behavior enables dietary shifts, habitat exploration, and social cooperation. In dynamic ecosystems recovering from collapse, such versatility proved advantageous. Mammals could exploit resources that became available unpredictably, adjusting foraging strategies and movement patterns in response to changing landscapes. The rise of mammals was not instantaneous or universal. For millions of years after the Cretaceous boundary, diversity expanded gradually. Some groups flourished briefly before declining, replaced by others better suited to emerging climates and habitats. Yet, across continents, mammalian forms diversified into roles once monopolized by reptiles, establishing new ecological architectures. This transition reflects the broader principle that dominance is contingent upon context. Traits that were peripheral under one regime can become central under another. The restructuring of ecosystems following extinction created conditions where small, adaptable mammals could radiate into prominence. Through incremental evolutionary change, supported by physiological and behavioral flexibility, they reshaped terrestrial communities. The story is not simply one of replacement, but of transformation. As mammals diversified, they altered vegetation through grazing, influenced predator-prey dynamics, and eventually, through one lineage, began to modify the planet's systems on a global scale. Their ascent illustrates how recovery pathways can redirect the trajectory of life, turning survivors of the margins into architects of a new era. Beneath clear, sunlit waters, coral reefs rise slowly, layer upon layer, as countless small polyps secrete skeletons of calcium carbonate. Over centuries and millennia, these structures accumulate into vast limestone frameworks, shaping coastlines and sheltering intricate communities. Reefs are both biological and geological, living surfaces anchored to ancient stone. Through deep time, reefs have flourished during warm, stable intervals when temperatures and ocean chemistry remained within narrow limits, yet they have also vanished repeatedly. The fossil record preserves thick reef limestones, interrupted by horizons where growth ceases abruptly. Entire reef systems that once extended across continental shelves disappear from successive strata, replaced by thin microbial mats or barren sediments. These gaps correspond to broader ecological crises when disturbances in climate and chemistry exceed the tolerance of calcifying organisms. Corals and other reef builders rely on a delicate partnership with symbiotic algae that live within their tissues. These algae perform photosynthesis, providing energy that supports rapid skeletal growth. Elevated temperatures can disrupt this relationship, causing corals to expel their symbionts and leaving the underlying skeleton exposed. Prolonged stress weakens colonies and reduces their ability to compete with algae and other opportunistic species. In addition to thermal sensitivity, reef organisms depend on seawater saturated with carbonate ions. Increased carbon dioxide dissolved in the ocean lowers pH, reducing carbonate availability and complicating shell and skeleton formation. Past extinction events often coincide with shifts in ocean acidity and temperature. During such intervals, reefs decline globally. In some cases, new groups eventually assume the role of primary reef builders, assembling different architectures from their predecessors. After the Permian crisis, for example, sponge and microbial communities temporarily dominated reef environments before scleractinian corals diversified and re-established expansive reef systems in later eras. Each rebuilding phase produced ecosystems distinct from those that came before, reflecting evolutionary innovation under altered conditions. Reefs function as keystones of marine biodiversity, supporting fish, invertebrates, and countless microscopic organisms. When reefs collapse, the loss reverberates across food webs and coastal environments. Sediment stability changes, nutrient cycling shifts, and adjacent habitats feel the consequences. The repeated cycle of reef construction, destruction, and renewal reveals both vulnerability and resilience embedded within marine systems. Modern observations offer parallels to these ancient patterns. Contemporary coral bleaching events, linked to rising sea temperatures, mirror stress responses evident in fossil records of past crises. Measurements of ocean acidity show trends consistent with increased atmospheric carbon dioxide, echoing chemical conditions associated with earlier reef declines. Though present day changes unfold within human timescales, they resonate with processes documented across millions of years. Reefs stand as living testimony to Earth's capacity for both fragility and regeneration. Their limestone foundations record intervals of abundance interrupted by moments of collapse. Each rebuilding phase demonstrates that life can reorganize and adapt, yet never in precisely the same form. In the rhythmic interplay of growth and disruption, coral reefs embody the larger narrative of a planet that continuously reshapes its living structures. In rocks now exposed along the frozen margins of Antarctica, impressions of leaves lie pressed between layers of sandstone and shale. Trunks once rooted in soil are preserved as mineralized wood, their growth rings still visible under careful study. These remnants testify to intervals when the polar continent was not a desert of ice, but a landscape of forests shaped by mild temperatures and ample rainfall. During parts of the Cretaceous and earlier greenhouse phases, Antarctica occupied similar latitudes to today, yet global climate differed profoundly. Atmospheric carbon dioxide concentrations were significantly higher, trapping more heat and reducing the temperature gradient between equator and pole. Under these conditions, temperate rainforests flourished near the South Pole. Fossil pollen and spores recovered from sediment cores reveal diverse plant communities, including conifers, ferns, and flowering plants adapted to months of winter darkness, followed by continuous summer daylight. Growth rings in fossilized wood provide clues to seasonal patterns. Rather than indicating severe freezing, these rings suggest periods of steady growth interrupted by low light winters, consistent with a cool temperate climate rather than one dominated by ice. Sediments deposited alongside plant remains contain evidence of freshwater systems and soils developed in relatively stable terrestrial environments. Together, these findings reconstruct a polar world far removed from the present. The transition from forested Antarctica to its current glaciated state unfolded over tens of millions of years. As continental configurations shifted and the Southern Ocean Gateway deepened, ocean currents reorganized. The establishment of the Antarctic Circumpolar Current isolated the continent thermally, reducing the influx of warm waters from lower latitudes. Simultaneously, declining atmospheric carbon dioxide diminished the greenhouse effect. These combined influences encouraged the growth of permanent ice sheets. Glacial deposits atop older forest-bearing strata mark this dramatic transformation. Layers of till and striated bedrock contrast sharply with the fossilized wood beneath, revealing a sequence from warmth to ice. Oxygen isotopes preserved in marine microfossils reflect falling global temperatures during the Eocene and Oligocene, aligning with the onset of extensive Antarctic glaciation. The story of polar forests underscores the sensitivity of climate to both atmospheric composition and oceanic circulation. Regions that now seem inherently inhospitable once supported ecosystems comparable to modern temperate zones. The movement between these states demonstrates the breadth of conditions Earth has navigated, shaped by interactions among tectonics, greenhouse gases, and solar input. Antarctic fossils stand as quiet witnesses to climatic transformation. Their presence does not imply permanence of warmth, nor inevitability of ice. Rather, they reveal that the boundaries of habitability have shifted dramatically across geological time. Within stone layers stacked beneath modern glaciers, the imprint of ancient forests endures, reminding us that even the coldest continent has passed through chapters of unexpected abundance. When extinction narrows the abundance of life, it does more than remove species from landscapes and seas. It compresses the genetic variation contained within those that remain. Populations that once numbered in the millions may shrink to scattered groups, isolated by geography and circumstance. Within these reduced communities, the range of inherited traits contracts. A genetic bottleneck occurs when only a small fraction of a species survives a crisis. The individuals that endure carry with them only a subset of the genetic diversity that existed before. Alleles, once common across wide territories, may be lost simply because their carriers did not persist. The future of the lineage is then shaped by this diminished pool, not by the breadth of possibilities that once existed. In the fossil record, bottlenecks are not directly visible, yet their echoes appear through patterns of reduced variability and sudden shifts in morphology. In living species, genetic analysis reveals signatures of past contractions, such as low heterozygosity or shared mutations indicating descent from a limited ancestral population. These markers point to episodes when survival balanced on narrow margins. Reduced diversity has immediate and lasting consequences. With fewer genetic variants, a population may be less resilient to new diseases or environmental fluctuations. Adaptation depends on variation upon which natural selection can act. When that variation is limited, the ability to respond to further change may be constrained. Some lineages recover diversity over time through mutation and recombination, yet this rebuilding unfolds across many generations. Bottlenecks can also accelerate evolutionary change in unexpected ways. In small populations, genetic drift becomes more pronounced. Random fluctuations in allele frequencies can fix certain traits more quickly than in large populations. Characteristics that were once rare may become common, not because they confer advantage, but because chance favored their retention. Over time, these shifts can differentiate populations and contribute to speciation. The aftermath of mass extinction likely included numerous bottlenecks among surviving groups. Early mammals after the Cretaceous crisis, marine invertebrates following oceanic anoxia, and plant communities after severe climate transitions all passed through phases of reduced abundance. From these constrained beginnings, new radiations emerged, yet they carried the imprint of their narrow survival. Bottlenecks thus represent both vulnerability and possibility. They reduce diversity, tightening the threads of heredity, yet they also set the stage for divergent evolutionary paths. A lineage that survives through a small remnant population may, over millions of years, give rise to varied descendants distinct from their ancestors. The loss embedded within a bottleneck shapes what comes next, steering the trajectory of life through contingency as much as through adaptation. Within the quiet mathematics of inheritance, extinction leaves a subtle legacy. Even when species endure, their genetic histories record the passage through constriction, a reminder that survival does not simply preserve what was, but transforms it in ways that resonate long after the crisis has passed. Across deep time, dominance has a way of appearing permanent while it lasts. Certain groups expand across continents and oceans, occupying apex roles in food webs and reshaping landscapes through their presence. For millions of years, they may seem untouchable, their fossils abundant in layer after layer, their influence woven into the fabric of entire ecosystems. Yet the record shows that no lineage maintains that position indefinitely. Ecological success often carries within it the seeds of vulnerability. As populations grow and spread, they consume resources at increasing scales. Herbivores alter vegetation patterns, predators regulate prey, engineers modify soil, water flow, or reef structure. When conditions remain stable, feedback mechanisms tend to balance consumption with regeneration. Over longer intervals, however, changing climate, shifting chemistry, or tectonic rearrangement can disrupt that equilibrium. Ecological overshoot occurs when a species' demands exceed the capacity of its environment to sustain them under altered conditions. This need not arise from overconsumption alone. It can emerge from specialization, when a lineage becomes finely adapted to a narrow set of circumstances. During stable eras, specialization enhances efficiency and competitive advantage. When thresholds are crossed, Those same specializations restrict flexibility. Traits that once conferred dominance may hinder adjustment. Limits of adaptation are shaped by physiology, reproduction, and genetic variability. Species cannot modify body plans or metabolic pathways instantly in response to rapid change. Evolution operates across generations, contingent upon existing variation. When environmental shifts outpace the rate at which advantageous traits can spread through populations, decline becomes more likely. Even widespread and numerous groups may find their tolerance ranges exceeded. The fossil record illustrates this repeatedly. Trilobites flourished for hundreds of millions of years before vanishing. Large marine reptiles dominated Mesozoic seas until abrupt extinction redefined marine communities. Forests composed of certain plant lineages expanded widely, only to retreat when climates shifted beyond their tolerance. Each transition reflects boundaries that dominance could not overcome. Control, in this context, is an illusion born of temporary alignment between biology and environment. A species may appear to command its surroundings, yet it remains embedded within networks of climate, chemistry, and geological change that lie beyond its influence. Feedback loops operate at scales larger than individual organisms or even entire clades. When these loops adjust, the parameters of survival adjust with them. The persistence of life across billions of years does not guarantee the persistence of any particular form. Dominance cycles through different groups as conditions evolve. Resilience emerges not from permanence, but from diversity and adaptability distributed across many lineages. In this shifting balance, control is never absolute. It is a transient state within a dynamic system, maintained only as long as environmental boundaries align with biological capacity. In the present era, extinction is no longer inferred solely from rock layers and fossil gaps. It is observed in real time, recorded through field surveys, satellite imagery, and genetic analyses. Amphibian populations decline in cloud forests, coral communities bleach across tropical seas, and large mammals retreat into shrinking fragments of habitat. The tempo of loss appears to exceed what paleontologists classify as background extinction, inviting comparisons to past crises documented in stone. Estimates of current extinction rates vary, shaped by the incompleteness of global inventories and the difficulty of confirming disappearance across vast and remote regions. Yet many studies suggest that species are vanishing at rates significantly higher than those typical of stable geological intervals. Habitat conversion plays a central role. Forests are cleared for agriculture and development, wetlands drained, grasslands fragmented. As landscapes are subdivided, populations become smaller and more isolated, increasing vulnerability to chance events and reducing genetic diversity. Climate shifts compound these pressures. Rising temperatures alter migration patterns and reproductive cycles. Species adapted to narrow thermal ranges face compressed habitat zones as conditions move poleward or upslope. Ocean warming and acidification stress marine organisms already coping with pollution and overfishing. In many cases, changes unfold rapidly relative to the generational timescales needed for adaptation. Invasive species introduce additional complexity. Organisms transported intentionally or inadvertently beyond their native ranges can outcompete local fauna and flora, introduce novel diseases, or disrupt established food webs. On islands, where endemic species evolved in isolation, such introductions have historically driven significant losses. The combined influence of habitat alteration, climatic change, pollution, and biological invasion creates a multifaceted challenge distinct from any single past driver. Despite these observations, scientific caution accompanies the term sixth mass extinction. Mass extinctions in the geological record are defined by substantial and global losses across a wide array of taxa within relatively short geological intervals. While current trends are concerning, some researchers emphasize the importance of long term perspective. Many species remain undocumented, and extinction is difficult to confirm definitively. Others note that the magnitude and speed of human driven change may warrant comparison with previous mass events, even if the full outcome has not yet unfolded. The debate reflects both urgency and prudence. Measurements of biodiversity decline, modeled projections, and conservation assessments contribute to an evolving understanding. Unlike ancient crises triggered by volcanic pulses or asteroid impacts, current pressures arise largely from the activities of a single species, expanding its ecological footprint across the globe. Within this context, the question is not solely whether present losses meet strict geological criteria, but how societies interpret patterns emerging now. The fossil record provides analogs of resilience and collapse. Contemporary data offer a snapshot within that broader narrative. Between caution and concern lies recognition that biodiversity is shifting measurably, and that the scale and trajectory of change carry significance for ecosystems still in motion. Long after forests thin and reefs crumble, long after large animals fade from familiar landscapes, something smaller remains. It persists in sediments, within pores of rock, along hydrothermal fissures where sunlight never reaches. The continuity of life on Earth has always depended less on its largest forms and more on its most microscopic foundations. Microbial life emerged early in the planet's history and has endured every transformation since. Bacteria and archaea inhabit boiling springs, acidic pools, hypersaline lakes, and the deep subsurface miles below continents. Their metabolic pathways are astonishingly varied. Some derive energy from sulfur or iron, others from methane or hydrogen released by geological processes. They do not require forests, reefs, or stable climates. They require chemical gradients and liquid water, conditions that have proven remarkably persistent. During mass extinction events, when oxygen levels fluctuate or temperatures rise sharply, many complex organisms perish. Yet microbial communities often shift rather than disappear. Certain lineages decline while others expand, adapted to altered chemistry. In intervals when oceans lost oxygen, anaerobic microbes capable of thriving without it proliferated. When surface environments became inhospitable, deep ocean ecosystems continued, buffered from rapid atmospheric change by the insulating mass of water above. Hydrothermal vent systems provide a striking example of this resilience. There, superheated fluids rich in minerals mix with cold seawater, creating steep chemical gradients. Microbes harness these gradients through chemosynthesis, forming the base of food webs independent of sunlight. Even during global climatic swings, vent communities likely endured, sustained by the steady heat of Earth's interior. Such habitats illustrate that life's foundation does not depend solely on surface stability. Extremophiles, organisms adapted to conditions once thought uninhabitable, broaden the definition of survivability. Some microbes tolerate radiation doses lethal to most life, repairing damaged DNA with efficient molecular mechanisms. Others endure desiccation for extended periods, reviving when moisture returns. In frozen environments, metabolic activity can slow to near dormancy, allowing persistence across long, cold intervals. These capabilities mean that even severe planetary stress does not equate to biological erasure. The durability of simple life lies partly in scale and simplicity. Microbes reproduce rapidly, generating variation across short time spans. Their small size allows them to inhabit niches inaccessible to larger organisms. When environments fluctuate, genetic diversity within vast microbial populations provides raw material for adaptation. Evolution proceeds continuously, quietly rebuilding complexity from resilient foundations. After each documented mass extinction, the fossil record eventually records renewed diversification. While dominant groups change, the underlying biochemical systems endure. Photosynthesis resumes, nutrient cycles reestablish, and ecosystems reorganize. The pattern suggests that as long as liquid water persists and energy flows from the sun or Earth's interior, life retains footholds from which to expand. This continuity does not guarantee preservation of particular species or ecosystems. It reveals instead that life, in its simplest forms, possesses a persistence deeply embedded in planetary processes. From microscopic cells clinging to rock pores to communities thriving in darkness beneath the seafloor, the architecture of survival rests on organisms capable of enduring conditions that unsettle more complex forms. There are thresholds beyond which even microbial endurance would falter. A planet can, in principle, become sterile if oceans were to boil away entirely, if surface rocks were baked to temperatures that denature complex molecules, or if radiation stripped the atmosphere and scoured exposed life. The chain of continuity could break. These scenarios are not imagined lightly. They arise from physics, from stellar evolution, and from the long trajectories of planetary change. Astrophysicists understand that stars gradually brighten as they age. Over billions of years, increasing solar luminosity will intensify evaporation from oceans, enhancing atmospheric water vapor, itself a potent greenhouse gas. This feedback could eventually drive a runaway greenhouse effect similar to conditions inferred for Venus. In such a future, surface water would be lost to space, and temperatures would rise beyond the tolerance of known life. Yet this transformation lies far ahead, on timescales measured in hundreds of millions to billions of years. Other sterilization possibilities include massive asteroid impacts or nearby supernovae. An impact large enough to melt significant portions of Earth's crust would release immense energy, potentially vaporizing oceans locally. A close supernova could bathe the planet in high levels of radiation. However, even the largest confirmed impacts in geological history did not eradicate all life. Subsurface microbes, shielded beneath kilometers of rock or deep ocean sediments, would likely persist through events that devastate surface ecosystems. Planetary habitability depends on a combination of liquid water, stable chemistry, and energy sources. Earth's position within the habitable zone permits water to remain liquid under present conditions. Tectonic activity cycles carbon between atmosphere and lithosphere, moderating long-term climate. The magnetosphere shields the surface from much of the solar wind. These systems create buffers against abrupt sterilization, ensuring that global extinction requires extreme and sustained disturbances. In the near term, measured in thousands or even millions of years, total extinction appears unlikely, based on current understanding. Mass extinctions documented in the fossil record removed large percentages of species but left microbial lineages intact. Even after episodes when oceans lost oxygen or continents were cloaked in ice, life endured in refugia. The resilience discussed earlier rests on diversity across habitats, from hydrothermal vents to deep crustal pores. Complete eradication would require not merely ecological collapse, but elimination of every viable niche where life could persist. Given the breadth of environments occupied by extremophiles, such elimination is difficult to envision without fundamental planetary transformation. Earth would need to lose liquid water or experience temperatures far beyond present extremes. Thus, while specific lineages may vanish and ecosystems may reorganize dramatically, the probability that life as a whole will disappear in the foreseeable geological future remains low. The planet's internal heat, protective magnetic field, and expansive oceans provide continuity that extends beyond individual crises. Life's persistence is anchored in processes that operate at scales deeper and broader than the disturbances that periodically reshape the surface. The word reset can suggest a blank slate, as if the planet periodically wipes itself clean and begins again from nothing. The geological record tells a subtler story. After each great disruption, layers above the boundary are not empty, they are different. Familiar forms vanish, yet traces of continuity thread quietly through the change. A reset does not mean total destruction. Microbial communities endure in sediments and deep crustal fractures. Certain plants, invertebrates, and small vertebrates persist in refuges sheltered by geography or tolerance. When conditions shift beyond the range of dominant groups, extinction narrows the field rather than erasing it entirely. What follows is ecological reorganization, not absolute beginning. Food webs reassemble from surviving components. Primary producers reclaim space, whether through photosynthesis in newly opened waters or vegetation spreading across disturbed ground. Herbivores diversify in response to available flora. Predators emerge to regulate expanding prey populations. The architecture of ecosystems is rebuilt step by step, guided by opportunity and constraint. Though energy still flows from sun and interior heat, the pathways it travels are rearranged. Dominance reshuffles in this process. Traits that once conferred advantage under previous climates or chemistries may no longer align with altered conditions. Lineages that were peripheral can assume central roles. After marine anoxic events, organisms tolerant of low oxygen become prominent. Following continental rearrangements, species adapted to isolation may diversify rapidly. Recovery is therefore directional, shaped by both inherited capacity and new environmental context. New winners emerge, yet they are not copies of what came before. Evolution explores configurations that reflect the selective pressures of the post-crisis world. Body plans shift in scale and proportion. Reproductive strategies adjust. Communities that appear stable for tens of millions of years may bear little resemblance to those beneath the boundary that preceded them. The continuity lies in life itself, not in specific forms. Calling this sequence a reset emphasizes pattern without claiming inevitability. The term captures repetition while acknowledging variation. Extinction events differ in magnitude and cause, and their aftermaths unfold along distinct trajectories. Some recoveries proceed gradually over millions of years. Others show bursts of diversification where ecological space is abundant. In every case, the result is not restoration of a former equilibrium, but establishment of a new one. The rhythm suggested by repeated reorganizations does not resolve into a simple rule. It reveals a dynamic planet where stability is provisional and adaptation is ongoing. A reset, then, is a phase of transition embedded within a longer continuum. It describes the turning of ecological structures rather than the end of life's narrative. Beneath the surface of apparent catastrophe lies rearrangement, as systems recalibrate and the balance of influence shifts among survivors. Viewed across deep time, Earth does not resemble a machine moving toward a fixed goal. It behaves more like a shifting equilibrium, a system held in motion by constant exchanges of energy and matter. Solar radiation enters, heat escapes, plates move, oceans circulate, carbon cycles between atmosphere and rock. Stability emerges not from stillness, but from balance maintained through adjustment. Dynamic equilibrium means that when one component shifts, others respond. If atmospheric carbon increases, temperatures rise, enhancing weathering of silicate rocks, which in turn removes carbon over long intervals. When continents cluster into supercontinents, ocean circulation patterns alter, reshaping heat, distribution, and nutrient flow. These feedback loops operate across different timescales, some rapid, others unfolding over millions of years. None allow the planet to remain unchanged for long. Collapse, in this context, can be understood as a moment when feedbacks overshoot or lag behind disturbance. Energy imbalances accumulate. Volcanic outpourings inject greenhouse gases faster than geological sinks can absorb them. Orbital variations alter sunlight distribution, amplifying ice growth or retreat. Biological processes, such as the evolution of oxygen-producing organisms, transform atmospheric chemistry, triggering cascades that reorganize ecosystems. When thresholds are crossed, the system shifts into a new state. Geological recycling underpins this dynamism. Oceanic crust forms at mid-ocean ridges and descends at subduction zones, carrying carbon and water into the mantle. Volcanic arcs release gases back to the surface. Mountains rise and erode, supplying sediments that lock away nutrients and carbon. These cycles regulate long-term climate and habitability. They also ensure that no configuration persists indefinitely. Continents assemble and fragment, seas open and close. Within such a framework, permanence becomes improbable. Species adapt to prevailing conditions, and ecosystems stabilize for intervals that seem vast relative to human experience. Yet, the underlying drivers continue their slow rearrangements. The apparent calm of a flourishing biosphere may mask gradual accumulation of change in atmosphere, ocean chemistry, or tectonic geometry. Eventually, the equilibrium recalibrates. To ask whether collapse is built into the system is to consider whether these recalibrations are exceptions or expressions of normal planetary behavior. The record of repeated transitions suggests the latter. Earth does not aim for destruction, nor does it safeguard any particular configuration. It adjusts. Energy flows must be balanced, chemical gradients must be resolved, tectonic stresses must be released. In this light, extinction events are not alien intrusions into an otherwise static world. They are phases within a continuum of adjustment. The biosphere evolves within parameters set by planetary physics and chemistry, and when those parameters shift, life reorganizes accordingly. There is no final steady state waiting beyond these cycles. There are only phases, each emerging from the interplay of forces that never entirely rest, each carrying forward fragments of what came before into patterns not yet fully formed. From the vantage point of deep time, extinction does not stand apart as an anomaly. It appears woven into the broader movement of the planet, like a recurring note within a long composition. Layers of sediment record intervals of abundance, interrupted by sudden thinning, then thickened again by new assemblages. In this repetition, Extinction reveals itself as transformation rather than finality. Dominance, when viewed across millions of years, resolves into a temporary arrangement. Marine reptiles, armored fishes, towering ferns, great terrestrial mammals, each in turn held central positions within their ecosystems. Their influence shaped landscapes and seas, yet their tenure was bounded. Shifts in atmosphere, temperature, sea level, or continental position altered the rules. When conditions moved beyond tolerance, the composition changed. Stability, too, carries a different meaning at geological scale. It represents a brief balance among opposing forces, maintained for spans that feel immense yet remain provisional. Carbon cycles moderate climate until inputs exceed outputs. Ocean currents distribute heat until tectonic changes redirect them. Ice sheets expand and retreat with subtle adjustments in orbital geometry. Each equilibrium persists only while feedbacks remain aligned. Earth itself is not hostile in intention, nor protective in design. It is dynamic, responding to energy flows and internal pressures with continual adjustment. Mantle convection drives plates. Volcanic gases modify skies. Weathering consumes mountains and returns their minerals to sea. These processes unfold without regard for particular species. Life evolves within their boundaries, adapting, radiating, contracting. Across every recorded crisis, some forms endure. Microbes persist in darkness and heat. Seeds wait within soil. Lineages contract and then diversify anew. Life proves persistent, yet never fixed. The organisms that repopulate a recovering world differ from those that preceded them. Evolution does not rewind. It branches outward from survivors, exploring possibilities shaped by altered climates and geographies. The quiet pattern that emerges is neither chaotic nor rigid. It is rhythmic. Expansion gives way to contraction. Contraction opens space for renewal. This rhythm does not imply inevitability of catastrophe at predictable intervals. It suggests instead that change is intrinsic to a planet governed by physics and chemistry in constant motion. Stillness is the exception. Within this understanding lies a calm recognition. The biosphere has endured asteroid impacts, volcanic floods, frozen oceans, and shifting continents. It has also relinquished countless forms that once seemed integral to its fabric. The continuity resides not in specific species, but in the capacity for reorganization. To say that change is the rule is not to deny beauty or complexity. It is to acknowledge that both arise within movement. Earth does not reset in anger or design. It recalibrates. Life does not vanish utterly. It reshapes. Beneath the apparent drama of extinction lies a longer, quieter continuity, a planet alive through transition, never static, always becoming something new.